Hello friends, welcome to video lecture on fluid mechanics. In the today's session, we learn about buoyancy and metacenter. So let's start with the buoyancy. When a body is immersed in a fluid, an upward force is exerted by a fluid on the body. This upward force is equal to the weight of the fluid displaced by the body and is called the force of buoyancy or simply buoyancy. Center of buoyancy is defined as the point through which the force of buoyancy is supposed to be act. As the force of the buoyancy is a vertical force and is equal to the weight of the fluid displaced by the body, the center of the buoyancy will be the center of gravity of the fluid displaced. So this will clear to you here. Okay, of buoyancy point and center of gravity point here, whatever the force acting here, fluid displaced by the body. Okay, this is nothing but buoyancy. So discuss oracle on the same point. Find the volume of water displaced in the position of center of buoyancy for a wooden block of width 2.5 meter, the depth 1.5 meter. When it floats horizontally in water, the density of the wooden block is 650 kilogram per meter cube and its length 6 meters. So if you just say the dimensions of the wooden block in front of you, but from this one, if you just see H indicate the height of this one to water surface, details available with us. Okay, now say the width with us 2.5 meter, depth with us 1.5 meter, with us 6 meter of the block is nothing but 2.5 multiplied by 1.5 by this 0.50 meter cube. So density of the wood with us rho equals to 150 kilogram per meter. Then here we can get the weight of the block, but the rho g by volume. So rho with us 650, g with us 981, and the volume with us 22 Newton. Okay. So the product of all this term can get 14,000, sorry, 1,13,000 and for the equilibrium, the weight of the water displaced, but the weight of the wooden block. Okay, for the equilibrium condition, for that weight of the water displaced, weight of the wooden block, okay, that must be equal. Okay, so therefore the volume of the water displaced, but the weight of the water displaced to the weight density of the water. We get here this term divided by density of water 1.81. Okay, can get 15.625 meter cube. Since we know here density of the water is nothing but 1000 I can get the position of buoyancy. Volume of the wooden water equals to volume of water displaced. For this one, 0.5 multiplied by height multiplied by this one length. Okay, so to equate this one from this, what we get here, get the height. Okay, height is nothing but here this term. For simplification, we get h to 0.975 meter. So center of buoyancy is nothing but half of this one. From the base, you can get 0.875 meter. The base. This base we can the center of the buoyancy. So let us start the discussion with the metacenter. Metacenter is defined as the point about which the body start oscillating when the body is hit by an angle. The metacenter may also be defined as the point at which the line of action of the force of buoyancy will meet the normal axis of the body. Body is given a displacement. Okay, this way. Now here just consider the body floating in a liquid as shown in this figure. Okay, let the body is in equilibrium, and G, here is the G, the center of gravity, and this one, the B, indicate the center of buoyancy. For the equilibrium, both the points lie on the normal axis. Here is the normal axis, which is vertical. Yet the body is given angular displacement in the clockwise direction. Okay, this way. The center of buoyancy, which is the center of gravity, body is submerged, will now shifted towards the right of the normal axis. The angular displacement in clockwise direction. Here, one of buoyancy, which is the center of gravity, which is the center of gravity of the displaced liquid, or center of gravity of the portion of the body submerged in liquid, now shifted towards the right of the normal axis. It is at B1. Here B and that this line of force buoyancy in this new position. This way you can get the line of action position. There is the new, will intersect the normal axis of the body at some point, say M point. This point M called Metacenter. Okay. Now my target is to get the metacentric height, distance mg. That is the distance between the center of the body and the center of gravity of the body, called metacentric. Now see the analytical method for the metacenter height. This figure shows the position of floating body in equilibrium, the location of the center of gravity and the center of buoyancy in this position at G and B. The floating body is given smaller angular displacement, okay, in the clockwise direction. This indicates the displaced diagram. The new center of buoyancy here, original here, new center of buoyancy B1. Okay. The vertical line to, here is the to B1, but the normal axis at point M. As M is the metacenter, and this GM metacentric height. If you just see this way, you can get that metacentric height. Now, the angular displacement of the body in clockwise causes the base shape prism to be on the right of the axis. Here we get that B O, here B O, here this one B dash, okay, towards the right side. Similarly, we can get the another wedge shape, that is O A dash A. A O A dash, okay, emerges out of the water on the left of the axis. These wedge shapes represents the gain in the buoyant force on the right side and corresponding loss of the buoyant force on the left side. Here we can get the gain, okay. Gain we can get in terms of this one, this force FB. Loss we can get with of another, okay, the same magnitude but in the opposite direction. Okay. So if you just here, the gain represented by the vertical force be acting to the center of gravity of this small prism like wedge. Okay. Similar actually opposite direction will adds to this one. What's about the two forces? That two forces will form pull due to this force to rotate the ship in the counterclockwise direction. Also, the moment caused by the displacement of buoyancy from B to B1, the counterclockwise direction. Here the in counterclockwise direction. Thus, the two couples must be equal. However, this one, now the couple, two parallel equal in the magnitude but opposite in the direction, separated by certain distance, that form a couple. Okay. Now, couple due to edges. Consider towards the right of the axis, a strip of thickness dx, distance x from O. Figure B, height of the strip x multiplied by angle BO A dash, get x multiplied theta. This distance plus x, and if you just see the distance theta angle with BO dash is multiplied this distance, get the height of that strip. Now, area of the strip is height multiplied by thickness. So, what's about the height multiplied by thickness? Height already you can get here with the help of this one, x multiplied by theta. What's about the thickness? Thickness we can get the dx. If L is the length of the protein body, then the volume of the strip is nothing but area multiplied by L. Area of this one, okay, that should be then L. Area with us x multiplied by theta. X, the weight of the strip is nothing but rho g multiplied by volume. Here rho g multiplied by, for the volume is here x multiplied by x multiplied by this theta multiplied by L multiplied by x. Similarly, if the small strip of the thickness dx at a distance x, the O towards the left of the axis is considered. We just see the left of the axis is considered. Then the weight of the strip will be rho g multiplied by this one x theta L dx. The two weights are acting in the opposite direction, hence constitute a. If you just see the couple, weight of each strip distance two weights. Here the weight comes for these two strips multiplied by distance. Distance can get distance the single actually. The distance with us x. Similar actually you can get the distance from this side. Okay, so x plus x. What we get, that is nothing but the arm of that couple. Get the moment you by that arm of the. Here the distance two weights. What's about that distance? X plus x. Weight already with us. Okay, so x plus x is nothing but the 2x. Just simplify. Here the 2, here the this part written as it is. Then the moment of the couple for the whole wedge. Here for the small portion we are considering. Whole wedge means you need to integrate this term. To do the integration of this one, okay, integration of 2 rho here theta L multiplied by dx. The moment of the couple due to shifting of center of buoyancy due to B1. Of buoyancy is due to B1. Then this one FB multiplied by B1. B is nothing but So whatever these force we are considered for the small portion of that string. Okay, for the entire, if I consider nothing but the FB multiply by BB1, B1 is distance at the BB1, BB1 distance here. From that, you can get the moment of couple due to shifting of the buoyancy into P1. Moment is the dot of force multiplied by distance. Okay, now if BB1, you can get B theta. Theta is very small, very small. With this BB1 with theta. Okay, but the two couples are the same for this and one. Then right, this term you have to equate with term W multiplied by BM multiplied theta equals to this one. Integration of 2 into L into dx. Now take this 2 rho g theta term here. Okay. Part remain. Write that part in integration sign. After that, just continue. Here, theta get cancelled. Then W multiplied by BM equals to rho g 2 into rho g into this term will remain as it is. Okay, now this L into dx is nothing but the elemental area on the water line in this figure. Okay, that must be equals to dA. Okay. Here is the line shown for discussion here. Must be equals to L multiplied by dx equals to dA. L multiplied by this one, L multiplied by this small portion dx must be equals to dA. So if you just see here this term again written as it is, and this L multiplied by dx must be equals to dA. So from this number C, there is a for C, it is clear that 2 into 1, 2 into integration of x square dA, the second moment of area of the plane of the body and surface about the axis yy. Therefore, of this term, just replace this one by I. This I is nothing but the second moment of inertia of the plane body at the water surface. Okay, about the yy axis. At yy axis. Now we get here W multiplied by B OG into I. After that, just say previous step. What that M is the rho g I divided by W. This term goes in denominator. So what's about W? W is nothing but the weight of the body, and weight of the fluid displaced by the body equals to OG body. This equals to the volume of the body submerged in the water. Okay, multiply. We can just represent by this one B. Get the merged body submerged in the water. So you just see here is nothing but the rho g by I. What's about this one? W is nothing but the rho g. Okay. This case, this what do we get here? I divided. What's about here? BM we get is nothing but okay here. So what's about this one? This GM is nothing but the GM is the total distance with us BM minus PB. Same is written here. Okay. So this BM with the I divided by this V minus PG. Metacentric height. Our target from this one to get the value for this one GM. This is nothing but the metacentric height. Now from this formula I can get the metacentric height, that is GM equals to I divided by V minus PG. This is the formula for calculation of metacentric height. Thank you. Hope that today's lecture points such as buoyancy, metacentric height are discussed clear to you. Thank you.